He's making this noise. Yeah.
No, sir.
Okay, okay. Thank you for coming. I don't know if everyone interpreted correctly that we would start at 2, but that's fine. It will be recorded. So yesterday I introduced a few basic principles for the design of simple PD and PID controllers, so on and so forth. And remember that I started with a plant, which I call the Nomoto model number 1, R dot equal to minus AR plus BU, who has rather deflection, or you can think in terms of torque that is generated, and then you want to control the R. And the conclusion that we reached was that if you want to stabilize and achieve steady state error equal to 0, then you are going to need at least, so this is the command, this is minus, this is the error. You are going to need feedback from R, because that's the thing you are comparing with the reference. And I call this gain K1. And then we introduced the integral gain. So K2 and then integrator. And remember what this was for, to drive the steady state error to 0. So this goes in here, this goes in here. All right. So I explained this carefully, I think. And then we talked about anti-windup that I'm not going to repeat now. For a number of reasons, this is not the best way to implement. Unfortunately, in many books and publications, you see this controller implemented in this manner. So sometimes you see it implemented in a slightly better way. I'm not saying why it is better, but then I can explain a little bit later. So where you have K2 and the psi, and then this guy, instead of going there, goes directly here. K1, and it goes there, and then there's delta, and then this is the same thing. In terms of stability, you see, there's a very fundamental concept that when you have a linear system, the concept of stability is independent of the inputs. Okay, so if you have this system without an input, and you start with a certain rate of rotation, and you apply this controller, it will go to 0. When you apply an input, then everything is well behaved. So for linear systems, the concept stability does not depend on the particular kind of inputs that you have. For nonlinear, it's a completely different business. Okay, so one has to be very careful with that. All right. And the other thing that I was going to say is the following: stability only depends on the following. You imagine that you go for a walk, you cut it here, and you start walking here. Boom, 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 boom. Don't worry about that guy. And you come back and you stop there. This system where the input is this guy and then the output is this guy is called the loop gain. It's weird, it has the name gain, but it is a dynamical system. And stability only depends on the loop gain. So obviously, if you do the same kind of operation, which is to start here and go around, and of course you have to go this way. At this point, you get minus K1 times R, minus K1 times R, and K2 times the integral of minus E. So you get exactly the same signal. So from a stability point of view, they are equivalent. There's no problem. There's a far better way of implementing this, and I'm going to tell you this because if you really want to get into practical stuff, this is the way we implement all these types of controllers. It has a funny name. It's called delta implementation. Okay? And it's a bit counterintuitive. For many practical reasons, when you have an integrator, it's very important to have it at the input of the plant. So you'd like to have something like this. Integrator, and then you go to the rudder deflection. Why is this important? For many reasons, but one of them is the following. If you want to commute between open loop and closed loop, what you do, you have the system running, and suddenly, boom, you connect the controller. If the controller is before this, and the integrator does the interfacing between your controller and the delta, the integrator smooths out any possible wild transitions. And in a literature, you basically are saying that you achieve, it has a funny name, Bumpless transfer. Okay, but if you move this integrator to the right, so if you think of this loop, K2 times the integral. Okay, fine, you put the key here, K2, and then times the integral. It's there, there's no problem, okay? And then you come here, you do the RC minus error. What about this one? Because this one is impacting on the activity of the rudder through K1 times R. So you cannot put it here. You cannot put it here because this is integral of K1 times R, not K1 times R. So what you have to do is some sort of trick. Oop. And you put the K1 here, oh, K1 here. But because you'll be going through the integrator, you cancel the integrator by doing a derivative. That's how you do this, okay? Now, for people that are seeing this for the first time, probably they will become very suspicious because there's a fundamental golden rule in control, which is, you see, you are canceling the integrator with a differentiator. And if you do this normally, if you have an integrator and then a differentiator, when you multiply or operate them together, it becomes the identity operator. But even inside, there's some dynamics. And in certain control systems, this will kill you because it is as if you were not seeing these dynamics. It can be shown formally that in this case, this will not impact on the performance and that will not happen. And now that you have the integrator isolated, you can apply the anti-windup here. This is how we do the implementation of our, and there are many other reasons why you need to do this. So that's called the delta implementation and the bumpless transfer. Okay, now let's get into a more difficult case. But first a word of warning, not warning. Let me call your attention again to something I said yesterday. If you have a system to be controlled, sometimes you call it a plant. And if you have a controller, sometimes we call C. This is the classical way of doing things. And if you have Y, doesn't necessarily have to be the non-automobile, it's something. And you have the Y command, sometimes you call R, and you do this, error and minus. Suppose this system is stable. I already gave you examples of systems that you stabilized. And this thing that you have here is actually what I mentioned to you before, the loop gain. So you can obtain in many ways. You can start here and you go around the corner and come back. That's LP. If the system is stable, and when you zoom into this combination of blocks, you see anywhere, either in the controller on the plant, so it was zoom in, you see an isolated control integrator done if YC is constant, then when you let times tend to infinity, y of t tends to this YC equal to a constant. So you have steady state error equal to 0. And this is a fundamental point. I mean, if you want something to have sometimes people call finite steady state error or steady state error, okay. Sometimes called static error. I like to call steady state error in response to fixed inputs. The integrator operates the magic of making this steady state error exactly equal to 0. And I explained to you how this operates. The integrator in the process of charging and discharging, when we reach steady state because we are stable, the integrator is capable of charging up to the level required to excite the input and have the value at the output be exactly equal to the command at the input. This is because the integrator has memory of the past. So in the end, when E is equal to 0, it is driving the integrator with 0, but it will keep the value that it learned. And that will drive the plant and make the output exactly track the input. Now, notice that in the example that we studied for the non-motor model number 1, the integrator was in the controller. And this worked out fine. There are situations where there is already one integrator in the plant. So we'll go for the non-motor model number 2. So the non-motor model number 1 is very simple. You have a vessel, you have deflection of the rudder or torque or whatever, and you are trying to control this variable R. Number 2, instead of trying to control R, you are trying to control the heading angle. Okay, assuming side slip is 0. So that's non-motor model number 2. Okay. So how do you go about designing a true controller for this ship when you want to control the heading? The ship is going north, now you want to go east, you want to go south, so on and so forth. So remember, we always start with R dot equal to minus AR plus BU. And this pictorial really are represented as follows: R dot, R, and then remember I have A, B here, and that's the non-motor model number 1. But I said, oh yes, I'm not interested in controlling R, I'm interested in controlling psi. But the derivative of psi is equal to R. So psi is the integral of R. So psi is the integral of R. And this is the non-motor model number 2. So in essence, they are essentially the same thing, except that you are trying to control, in one case, the heading rate, in the other case, the angle of heading. Okay, so motivated by what we learned before, you could say, well, my feeling is that if I give it a command here in psi, and I compare, this is psi, okay? And I compare with the output, and a very simple control scheme is to have here a K that I'm going to call P. Then I could try and do this. When you look at this system, what you see? You see one integrator, two integrators. You have to start reasoning in intuitive terms. You have two integrators, so you have a second order system because you have two integrators. And when you close the loop, you have a second order system. So you may suspect, as I mentioned to you, that if you have a second order system and you only have one tuning knob, it will not be able to control independently the natural frequency, the bandwidth, and the damping factor. And I explained this, I hope, carefully enough. I mean, you have a second order systems, you have two things to tune, the omega n and the psi, and you only have one parameter to play with. So you need another one. Remember, when we examine a system like this, Kp is the equivalent of the spring. Why? Because Kp multiplies an error. And when you go to the mass spring dash pot, the spring is a term that multiplies the elongation, the deviation. So that's the equivalent here. So the other term should have to do with damping, the equivalent of the dash pot. So how do you introduce another damping? That's what I mentioned to you before. Damping terms are proportional to derivative of the variable. So you put another term here that you call Kd, and you add them up. And now you have two parameters that you can tune to achieve the omega n and the psi that you wish. So this is sometimes called the proportional plus derivative controller. So that's what you have. Now let's see what happens here. Oh, guys, I have a hard time. Ah, I got it. Okay, so what do you have? R dot equal to minus AR plus BU. And then psi dot equal to R. That's the top thing. That's the Namoto model. Number two. Okay, so yeah. So the derivative R is psi dot. Therefore, R dot is psi second derivative. So you put here second derivative is equal to minus AR plus BU, which is minus AR, sorry, minus A psi dot plus BU. But now U, which is this U, is equal to minus KD times R, minus KD times R, plus KP on top, psi C minus psi. Okay. So if you put this in there, then you get psi 2 dot is equal to minus A psi plus B KP psi C there's something fishy here. So let's see. R dot equal to minus R plus PU, psi dot equal to R. This is perfectly okay. This is the same thing. And U is equal to minus, let me KDR plus KP psi minus C. So you have psi dot equal to minus, sorry, biology. Okay. So there's a term here that is a bit funny. Yeah. So okay, so first I'm going to capture this one, right? So minus B KD psi dot plus B KP psi C minus B KP psi. So that's what you get from there. Okay, so very close to the end. So after you massage this, you get psi dot, psi double dot. Now you pass the psi dot terms to the left. So this one and that one go to the left. So you get plus I A plus B KD psi dot. Then now you have this term in psi to the left plus B P psi. And then you have this one that stays on the right. So you see here, your system has the input equal to psi C, and the output is the angle psi itself. And this is a second order system. So if you refine again, if you remember the general form of a second order system, this should be something like 2 psi omega n psi dot plus omega n squared psi equal to something that doesn't matter. So you see, if you can tune this KP and KD, if you can vary them, you can control this term and you can control this term. Therefore, you can tune KP and KD using a simple algebraic relationship so that you can control psi and omega n. You can do that. So that seems to be a decent design. And then of course, oh, there's someone here. All right. And there's something else because okay. There's something else. Now, if I ask you the question, is the system stable? And the question is, yes, of course, because this is the second order system. All the coefficients are positive. The system is stable. And when you look, if you start, for example, here and finish there, there's an integrator that is isolated. This guarantees that the static state error is exactly equal to 0. But pay attention to the fact that now the integrator is on the plant itself. It's the fact that psi is the integral of R. It doesn't matter. The integrator could be on the plant or inside the controller, no matter where it is. If when you go along this path, you find an isolated integrator and the system is stable, careful. Some people are led to the conclusion when they look at this, oh, this thing has steady state error equal to 0. If the system is stable. So if the system is stable and you find the controller anywhere, the static state error, static error is equal to 0. So it's a good bond. So this seems to be a relatively good design. I believe this is the controller that you have, right? This is a PD controller. It's a P and it's a D. Excuse me? No, inside it's the plant itself. This is the Nomoto model. This is your plant. This is your ship. And now you have feedback from rate, and you have feedback from angle itself. So you have P and D. So in this case, you don't need to implement anti-windup because you don't have any integrator there. Okay. Now, now suppose someone tells you the following. Okay, as I mentioned, for the Nomoto model number 1, it may very well be that when you install the rudder, there is a misalignment. And the same happens if you have a ship with 2 thrusters at the back, and you think that they are positioned in such a way that when you actuate them with the same RPMs, the overall torque is 0, but they may be slightly misaligned, and you don't know very well what the misalignment is, and you don't want to waste your time just making measurements. So it may very well be that here, when you think that you have 0, because you set the rudder to 0, and the local controller, in fact, because it's biased, there's an offset there, the rudder will deflect. So this means that you have a constant torque that will appear. So I'm talking both in terms of rudder deflection or torque, because I'm assuming they are related through a very simple relationship. So what's going to happen is that you end up having what we call a disturbance, which is a constant disturbance, because you are running and the rudder is offset. It's creating a residual torque that you'd like to eliminate, but it's there and you don't know exactly what the misalignment is. So there's a disturbance. And now you have to ask the question, is the control system capable of killing this disturbance? So what do you want? You can carry out a thought experiment where, for example, you tell the ship to go north. This is 0. Okay. So what will happen is that if you use this control law and there is no offset in the rudder, and if everything goes smooth, you'll go north. But if there is a bias there, then it will start turning. So you would like for the impact of D on psi to be eliminated. That's what people call disturbance rejection. You'd like to achieve disturbance rejection. So how can we do this? Use exactly the same reasoning that I mentioned to you before. This won't do the work. This thing is going to impact on the output. So it's going to turn to a certain angle, where and in fact you want it to go up north with angle equal to 0. You have to find an element such that with the error equal to 0, the element will learn how to produce at the output exactly minus D to cancel that D. So again, what is the element that is driven by 0 that will be able to generate a term that will kill that guy exactly? That's an integrator. So you have to do this control architecture and put an integrator there. So, this is always very hard to catch this guy. So you have to put an integrator. So you have the Nomoto model number 1. So that's R. And then you get the Nomoto model number 2, that's psi. And here you have the reference. and then you go there, right? Now, this is the error, and you already have this term that I'm going to put here, KP, and they go in there. And also you had feedback from derivative feedback. Can put it there, okay? But now you need something else. You need an integrator. So you go there and put KI integral, and you bring it there, and boom, okay? This will do the trick if the system is stable, okay? So now you can go through the same reasoning and ask the question, is the system stable or not? How can I check that? But it's easily seen that because you have an isolated integrator here, yeah, very, very important, very important. You see, I told you that when you have an isolated integrator, the static error is equal to 0. So this integrator by itself gives you static error equal to 0. But now, if you have a disturbance kicking in, the element that is going to learn what amount is required to inject here. So you see, when you reach steady state, you have PC psi c equal to psi. So this is 0. This is 0. And suppose you are going north, this is 0. The integrator will have at the output at steady state minus d, that will cancel that t and will drive the no-motor model. That's how it goes. So now I'm using the integrator for something slightly different, which is to kill a disturbance. So in the past, I used the integrator to achieve steady state error equal to 0. Now I'm using an integrator to achieve complete disturbance rejection. And the rule of thumb is you have to have the integrator before the disturbance occurs, because you have to be able to generate the bias that will cancel the term that is ever present. So this is a rule of thumb. So now the question is, how do I design KI, KP, and KD? So now you have what we call proportional, integral, and derivative controller. That's what people call PID controller. So I'm not going through the horrendous process of deriving the differential equation of order 3, because you have one dynamic element, another dynamic element, and the dynamic element inside the no-motor numbers. You have order 3. And believe me, when you write this, you get this horrendous thing. Third derivative, A plus B, KD, plus BKP, EIPC, equal to something at the input that does not matter. Now, okay, now we have a problem because this is a third order system. When you have a second order system, for example, psi dot plus A1 psi dot plus A2 psi equal to something. Even if you have never learned this, the conclusion is very simple. If all the coefficients have the same sign, this is a stable system. Stable in the sense that if you drive it with 0 and you start anywhere with any psi and psi dot, they will converge to the origin. And in the sense that if you input a constant, then psi will go smoothly to a finite state value. So for first and second order systems, if it's a necessary and sufficient condition for the system to be stable that all coefficients have the same value, the same sign, okay? For example, if you have R dot plus AR equal to U, this is positive, you are stable. second order. This is positive, positive, positive. You are stable. What happens when you go to a third order system? It's a necessary condition that all the coefficients have the same sign. So if you find a coefficient that is negative and the other are positive, forget it, it's unstable. But it's not a sufficient condition. You may have all the coefficients positive and still be unstable. So how in the heck are we going to see if this system is stable or not? Okay. So there are several ways of doing this. Computing the roots of some polynomial, stuff like that. But the problem is at some point you are losing the intuition as to what is going on. I mean, it used to be beautiful because you could relate to damping and the natural frequency. Now that is sort of gone. So, and that's why I'll introduce later in the class a method that will allow you to compute these gains here so that you get very good behavior for the system. And it will allow you to deal with systems of order 3, 4, 5, 6, 100. So it's a beautiful thing. Chat. Yeah, here when I talk about stability, it's always asymptotic stability, okay? Thank you. All right, so what else did I want to say? So how do you tune the parameters? Okay, so when you have this design, yeah.
So here in the plant itself, we have a integrator. So that takes care of my.
That would guarantee by itself that the static state error is 0 if the system is stable.
But if you use PID controller, it itself has an integrator. So irrespective of the plant, if it has an integrator or
yes,
this will take care of my steady state error.
Yes. No matter where the integrator is, controller or plant, if the closed loop is stable, steady state error is equal to 0. Okay. Let me comment on this because it's something very interesting, actually. So if you excite the system with a step, and this system is complex, right? It's a controller. I'm writing in this abstract form. The plant, the output, the error, and the input, sometimes people call the reference. And ask the question, suppose the system is stable. Does the output tend to the input? And the answer I gave to you is yes, if the system is stable and you go from here to there and you find at least one integrator, you are done. It's another interesting question because especially in robotics, manipulators and stuff, sometimes you want the tip. So here I'm imagining things a bit. You don't want just the tip to go from place. Sometimes you may wish to follow, for example, a ramp for a certain. So the other interesting question is, if R is a ramp, and you'd like for the output to follow this ramp, so you'd like for it to do something like this. So this is the input, and suppose you start here, and you'd like for the output to follow the ramp. Okay. You can do this if you have at least 2 integrators in the loop. And you can do the same for a parabola. So this is t, this is t squared, and this is to 0. So Degree 0, you need 1 integrator. Degree 1, you need 2 integrators. Degree 2, if you want the output to track this parabola, you need 3 integrators. So one may lead to believe in the following statement. So I'm going to be a bit abstract here now. If you want for your system to track a signal that is quite rich, so instead of a constant, so here is a very simple, naive statement. You have heard the Weierstrass theorem, right? I don't know if you know that by that name. So any function sufficiently behaved over a finite interval of time can be approximated in some sense by a sum of polynomials. So you could say, well, if I'm interested in tracking signals that are complex, but for example, are described by a sum of polynomials up to degree 5, then you have 6 integrators and you are done. Wrong. Because the more integrators you have in the loop, the more difficult it comes to stabilize the system. So that's the price you pay. So one has to be careful about that. All right, now, of course, there's another detail there that we can go into, which is now that you have, and incidentally, this is the control system that we use for our vehicles at the surface or underwater when you want to control the heading. This is exactly what you use, except that at some point, we are going to implement the anti-windup. So again, we do the trick. We move. Oh, no, I can't. We move the integrator in front, keep this gain, differentiate that one, not differentiate that one, differentiate that signal and differentiate that signal, as I did before. So with the delta implementation, it's going to work very well. So, all right. So we have seen how for simple systems like Nomoto model number 1, if you want to control R or if you want to control psi, but without having the rudder having an offset, we know how to do the design and then implement and use anti-windup. If you go for Nomoto model of order 2 and you want the bias in the rudder and you have to introduce another integrator, you get this complex system. You don't know if it is stable or not. And in fact, it may be hard to decide how to choose Ki, Kp, and Kd. I mean, you can go by trial and error, but it's always a bad choice. You should be smart about it. So the second part of the talk has to do with the introduction of a general method that will allow you in a very elegant manner to compute these games so that you satisfy certain criteria. But before I go there, let me give you a brief summary of very important things. So summary of steady state errors and disturbance rejection. Okay. So if you have the controller and the plant and you look inside and somewhere you can identify an integrator, as I mentioned to you. So the reference, this is Y, error, then the steady state error. If the system is stable, this is equal to 0. It's nice and clean. And this integrator doesn't have to be in the middle. It could be there, as for the Nomoto model number 1, or it could be on the controller itself, as I mentioned to you. There's the other very basic result that I mentioned to you. If you have something here and you have a disturbance, and you have an integrator here as I showed to you. And then you may have even more complex stuff here from the controller. If this system is stable, because you have an integrator here, you could have another one there. The static state error is equal to 0. And because you have an integrator before the disturbance, you will kill the impact of that disturbance. So you reject completely D. Sometimes you see systems in which the disturbance is at the output, D. Okay? And you have a controller, the plant. If you have a controller anywhere before that disturbance, then you get again SSE equal to 0 and reject D. But now be careful. You may have a system that rejects disturbances at the output, but does not reject disturbances at the input, because, for example, you could have the integrator on this side. And in this case, when the disturbance kicks in, you don't have an integrator before, you will not be able to kill that disturbance. So these concepts are very important. You put the integrator at the point before the disturbance, so that the integrator learns automatically what value to generate to kill the disturbance. Okay. You see, this is a very important thing. Okay. So it's always hard to catch this guy. Okay, so if you have a system with a disturbance at the output, normally disturbances don't occur at the output, because like if you have a system that is actuated by a torque or a force, the disturbance occurs there. But there are circumstances where it's nice to think in terms of the equivalent disturbance at the output. For example, when people do ship maneuvering under the influence of waves. I don't know much about that, but to assess the impact of waves on the motion of the ship can be quite complicated. And some people, what they do, they go to the model of the ship and they add a disturbance at the output, so that when you watch the whole simulation, it is as if the vehicle were being wiggled about. So it occurs at the output, but normally it's physical, it's not very physically sound. So when you have a controller plus the plant here, okay. There's one thing here, because this is a linear system, the principle of superposition applies. I don't know if you know about that. So when you have a linear system and you are trying to study the impact of D and R on Y, you can study both of them separately. So it's separation principle. That's what linearity means. So what do you know? If you have an integrator here somewhere, isolated integrator, what do I mean by isolated? For example, if you encounter an integrator that has a local feedback, this is not isolated. Okay, the integrator has to be isolated in order to be able to exert its action. So if you have an integrator somewhere, you have steady state error equal to 0, and Because the integrator appears before the disturbance, it will learn the value that is required to drive the output to the negative of this thing so that in the end it will cancel. But it may very well be that you have a system that has an integrator here somewhere, and you have a disturbance here. As I mentioned to you in the case of the no-motor model, number 2, the no-motor model has an integrator that comes from the physical plane. So in this case, so that's whatever. When you do this and you have some control law here, if you don't you need an integrator here to learn how to make this point go to minus, to kill the D and give you 0 there. So that's the essence of the thing. Always put the integrator before the place where the disturbance occurs, okay? So what else before we start with the other thing? Yeah. To use a different? Yeah, but you have a problem. You have a problem because if you put a differentiator here, right? Is that what you mean? It's going to kill this guy. But now you are differentiating this control signal and you have designed your system nicely to be stable, and God knows what happens when you put a derivative term there, you see? Of course, you may have, suppose you have a proportional and derivative control law, right? This derivative term, well, it cannot go there. You could do the derivative here. This derivative will not cancel that guy. So the derivative would have to appear here. You cancel that one, but then you also change the characteristics of the stabilizing signal. So more than likely your system would go unstable. So you can't do that. You can't do that. Is that clear? Okay.
So if we put an anti-windup system, so aren't we introducing a feedback to the integrator?
Yes, but it only kicks in. Okay, so let's do that. When you hit saturation and you wish to do, oh, I thought I had a diagram here with this thing. Doesn't matter. And you wish to do anti-windup reset. Yeah, it's here. It's because you are in a desperate situation. It's because you saturated. When you saturate, you no longer have a linear system. All hell breaks loose. All the analysis that I did was assuming that the system is linear. And therefore the integrator is independent and whatever. When you are closing that loop to try and bring the integrator down or up, it's because you enter this no man's land where you don't know what's going to happen, and everything goes. Hopefully it will go. It will be in your favor. So let me draw. Why is it so complicated? Aha, finally. So let's see if we can make some sense out of it. So you have the no-motor model number 2. So remember you have psi, and here you have delta. Or you can think in terms of torque. It doesn't matter. U, she's a torque. Now, please pay attention to the fact that when you want to excite this with a torque, for example, I want this to be certain Newton per meter, -1. And the system will tell you, no, my motor will not allow me to do that. So inside the plan, you have something that we have not taken into consideration, which is a saturation. So what does this mean? There's this tunnel here, such that if you keep working inside the tunnel, it's business as usual. The system is linear. The moment you touch the boundary of the tunnel, then you saturate here to plus and then to minus. So remember, there's something out there. So now I'm going to implement the PID controller. So in this case, it's psi. So remember, I have a derivative term. That comes from R, right? And then you have a proportional term that comes from psi. And instead of putting the proportional term there, multiplying E, for example, for the benefit of stabilization, it's exactly the same. I have Kp. And then, so I could do this. I don't want to make a mistake here. And then I have the integrator. Okay, this is the design that I came up with, right? So now you do the following. And this is again what we use in our systems. I told you, and I don't have time to get into this, that it's really beautiful to have the integrator at the input. So you move this guy there. So of course you have to extract it from here. But you have an integrator here. So now you have to do the derivative of this signal. And now you have to do the derivative of this signal. This is the famous delta implement. There are many, many reasons why this is useful. Now that you have the integrator isolated, you look here. Look at the integrator. And now I wish to use exactly the same nomenclature that I used before. So let me go back here. Yeah. So if everything is nice and easy, this signal will not saturate and this is stable and it's beautiful. Suppose now that you start hitting the saturation. If you hit saturation by the reasons that I mentioned to you, when you hit saturation, essentially you are in open loop. And the integrator is going wild, charging and charging because the error is finite. And then it's a pity because then it has to come down and induces these wild oscillations. So what you do is very simple. On your computer, you build a replica of this block. Okay, you build this. And then you compare the true value of your control law with a saturated value. If you are inside the tunnel, this value is exactly equal to that one at all times. You are not hitting saturation, you get 0, you do nothing. But if somehow the integrator, so for example, suppose this is 10 Newton meter, and you want 20 Newton meter because the integrator went wild. You have a positive difference. So you have to tell the integrator, please don't start charging up, just come down. And then you put the gain here. This is the tricky part that tries to discharge the integrator. And then you are back there. So this point is here and that point is there. That's the anti-windup. okay? So this is exactly how we implement our control systems for this still relatively simple control problem, which is controlling the yaw in the Nomoto model number 2. That's how you do it. So now that we have learned all this, we still have the question, how are we going to design, in this case, of Nomoto model number 2, and wanting to kill any disturbance at the input, how do we design the 3 gains? Because it becomes a bit messy. It's not a second order system. The intuition is gone. So how do you do that? So I'm going to stop for a little bit, maybe 10 minutes or so, and then we'll wrap up with the second part that has to do with the introduction of this beautiful method called LQR, linear quadratic regulator. This is a tool that will allow you for linear systems, for some linear systems, to do the design even when they are extremely complex. You still use your intuition, but then you don't have to do many manipulations because you have a beautiful mathematical solution, and then MATLAB will do that for you. But you have to use your engineering judgment. It's not a blind thing, okay? All right, so let's stop for approximately 10 minutes and then we'll come back. Are there any questions? Oh, there's a question here. That's Avanish. This is excellent question. So you are computing the derivative, of noise. And you know, if you have noise and you compute the derivative, it goes even more bananas. It can be shown formally using the delta implementation because you have the integrator up there. Yes, locally inside your, so you have to be very careful with the size of the words, the number of bits or bytes or whatever. It will introduce some noise, but then the integrator will filter out. So this has been shown formally in a paper that I can mention to you. This was long ago. That's a paper that there's a story behind this. So when I was studying under Professor Pramod Khargonekar, there was a good friend of mine that was a student at the same time, and he went to work for Boeing. And at Boeing, they were dealing with systems of this kind. And there was a gentleman there by the name of Ed Coleman that then designed some of the controllers for the Boeing aircraft. And he had this trick of moving the integrator. We did not discover that ourselves, but he never made the computations. He knew it will work very well. So we sat together with Ed Coleman and made it formal. And in that sense, we were very successful. We did not invent anything new. We just formalized and we showed in the paper that this works very well. And even when you have noise, it does not introduce further amplification, which is a beauty. Is that okay, Avanish? I guess so. Okay. All right, so for about 10 minutes, okay? All right. So, yeah. Huh? I can go there myself. Okay, thank you. I don't know if Professor Suresh will come or not. Yeah, it's okay. All right. But it says that you cannot hear me. Avanish, can you hear me? Yusen, can you hear me? No. All good. Thank you. All right. So you have a thing rotating about one axis with angular velocity omega. Why? Because you apply a torque. So this is in outer space. And then you know that the torque, in this case, it's trivial. It's the moment of inertia about the z-axis because it's rotating only about the z-axis. Times angular acceleration. So you don't have all that business of it's my allergy. I don't have COVID, don't worry. The gyroscopic terms and stuff. So I'm going to make I equal to 1 in the corresponding units. So in control theory, when you go to a more abstract level, you should have different letters. Oh, sorry, the same type of letters for identical types of things. So the variables, the things I want to control, to observe, sometimes are called X. So in this case, I'm making X equal to W. And the inputs through which I can control the system, normally we call U. So U in this case is the torque, okay? So the model is extremely easy. It's the derivative of X equal to U. So the derivative of angular velocity is equal to the torque, except that they use this notation that is pervasive in control theory. So this is also what we call an integrator, right? It's a simple integrator. X dot equal to U here. So suppose you have this satellite or whatever tumbling, not tumbling, it's just rotating about one axis, and you want to kill the rotation. How do you do that? Suppose you want to bring the speed of rotation down to 0. So based on what we did here, maybe a simple control law will do the job, which is U, I mean, it's such a simple system, equal to minus K X. And in fact, when you replace here, you get X dot equal to minus Kx. So you get that X of t is equal to the initial e to the minus kt, t greater than equal to 0, and you stabilize the system about, exponentially stabilize the system about the origin. All right. So now let's think a little bit about this. If you want, so suppose you are starting at x naught, so it's spinning it at a certain speed of rotation, and you want to bring it down to 0. It's clear that if your k is small, and it's going to take a long time. And as k increases, you get faster and faster. Well, this is asymptotic. This is k increasing. This is obvious. So what you wish to do is to bring the system to the origin relatively quickly, but now you have to be careful, because if you have restrictions on the energy that you can spend, then you have to be careful. Because here, suppose the energy is somehow quantified, I mean, it's not exactly the case, but by U square, which is K X square. Okay. So we'll do this. K square x squared. All right. So let's do this. So on one hand, you want, let me raise this because it may create confusion at this point. So on one hand, you want to bring this to 0 as fast as possible, asymptotically. On the other hand, you don't want to spend too much energy, okay? Because you see here, maybe I shouldn't have erased it, u squared is equal to k squared x squared. So as k increases, your input square pumps up, so you are going to spend more energy. So the first thing you want to achieve is to make the curves, the trajectories go to 0 very quickly. So if they go to 0 quickly, so let's compare these two things. So you have this case, or you have this case. So this is x of t. So in this case, the k is so large that you boom, you go very quickly to 0. So if you compute, for example, the integral between 0 and infinity of x squared of t dt, so you have to raise this to the square and do the integral, this will give you a very small area. Whereas if you stay away from the origin and end up there and slowly evolving towards the origin, when you square this, then you get a very large area. So it seems reasonable that if you want to formalize this, you should say, I would like to minimize the integral between 0 and infinity of x squared dt by proper choice of the control law. That's one thing you wish to do. But now someone tells you, hey, you have to be careful, because if you only have this condition, the system, if you pose this in a mathematical, using a proper mathematical framework, it may very well be that the solution will come up something like this. And then it's obvious that if you make this number very small by speeding up, then that's because you pump up the k, and then you end up spending a lot of energy, if energy is measured in this sense. So be careful, because at the same time, be aware of the energy that is spent in the process. And then, without being too sophisticated, you could say that you measure the amount of energy or something related to the energy spent by computing the integral between 0 and infinity of u squared of t dt. And this is the energy spent. So now you have this trade-off. If you want to make, according to this solution, which may not be the only possible one, if you want to make this, the state be attracted to 0 very quickly, you have to pump up the gain. And then because u squared is k squared x squared, you may end up spending a lot of, or wasting a lot of energy. All right. So, okay. Now, you could start being sophisticated here, and mathematical say something like this. I want to minimize by proper choice of u this thing that tells me if I'm going to converge slowly or not to the origin, under the constraint that the energy that I spent is less than a certain number gamma. Okay, this is a more difficult problem. Because you probably have heard of optimization problems, right? But now you have two criteria here. So sometimes people call this the multi-cost, multi-criteria optimization problem, because you are trying to minimize the deviation from zero and at the same time minimize energy. So you have to have some compromise. And some people attack this, and in some cases it's rigorous to attack it in this manner, which is you do a salad. You mix the two types of criteria and you say, well, why not look at a criteria? So this is very important now. I'm going to mix them up, and I'm going to try and minimize a criteria that I call J. This is a scalar by proper choice of U. And now pay attention to what I am going to do. You put here the X square, you put the U square, this is the penalty penalty on poor performance. So if it takes a long time to come back to the origin, this number will be big. And this is the penalty or cost on energy spent. But you cannot mix oranges with apples. So you bring in a scalar that I call rho greater than 0. And I say the following. When rho tends to 0, I basically am not paying attention to the energy that I'm going to spend. So the energy is cheap. If the energy is cheap, a natural solution will be to crank up the K, boom, go very fast. So this is cheap energy. When rho increases, they are putting a lot of attention into the process of minimizing the energy that you spend. And this is expensive energy, expensive energy. So right there, you have your engineering judgment. So when you formulate the problem, you have to select the rho. And we'll see how we can select this. Now, pay attention to this. Yeah, okay, so what's the strategy? Let's compute J, which is the integral between 0 and infinity of x squared. So I'm not going to write x squared of t plus rho u squared dt. Okay, so in this particular case, I'm not saying it's the only solution, because you have x of t equal to x of 0 e to the minus t. Okay, and because u equal to minus k x of t, so you get x squared of t 1 plus, I won't use the same notation here. 1 plus rho k squared dt. So the only thing I'm doing is the following. If I select a certain k, and I still don't know what's the best k. If I select a certain k, and if I start from some x naught, what is the combined cost of this thing? So when you perform this integral, you get x0, which is the initial condition, 1 plus rho k squared over 2k, all right? And this function is going to look like this. So there's a certain point, which is k star, for which you get the minimum, okay? So this is a very interesting graphic, because it tells you that when you fix as a function of k, when you move this k, this criterion here and for a certain x naught, this is what you get. Okay. Man, this is difficult. Okay, here you go. So what is this optimal value for which the criterion is minimum? So the thing you have to do is to compute the derivative of j with respect to k and make it equal to 0. So when you compute this derivative and make it to 0, you get k. So I'm not going to write the computation, instead in notes, 1 over rho. And this tells you a very plausible thing. If rho is small, that's what I call the cheap energy, then the gain will be very large. You can use all the energy in the world and you go boom, like this very fast. This is asymptotic. If the energy is expensive, then k has to be small and you have to allow more time to go back to the origin, right? So now notice the interesting trade-off. There's a trade-off here. So if you compute, I don't know if you are used to this notation. You know what this means? The norm of a function? No. Huh? It's the integral of the square. Okay, all right. Which is the integral between 0 and infinity of x squared dt. Then you get x0 squared over 2k if you do these computations for a certain k and for a certain x naught. If you do the same for u, then you have the integral between 0 and infinity u squared t dt, and then you get x0 squared k. And if you compute the ratio of the two, x, I believe over u, yeah, you get, so the x0 square, they cancel out, so you get 1 over 2k divided by k, and you get 1 over k squared. So this leads you to a very interesting diagram where you have, let's say, the energy associated with u, the energy associated with the error, and you got something like this. This is the famous trade-off curve that tells you if you want for the system to go very quickly to the origin and thus have this number small, you have to pump up the energy. If you wish to have the energy very small, you have to allow the system to be more sluggish and take longer to get to the origin. And if I ask you the question, for a particular initial condition, if I want to do the maneuver without this exceeding a number, what can I do? So this is, oops. Something wrong here. So if you don't allow for the energy to be larger than a certain number gamma star, immediately you have to pay a price because the integral of the error has this value. You cannot decrease it any further. There's an interesting name associated with this that originated in economics. And this is the Pareto optimal or Pareto boundary. Because they have very complex problems in economics, or they play with several variables, and it's very important for them to examine the trade-off. Okay. All right, so we know that if we are trying to design a controller for this very simple system, which we know how to do, I mean, this is trivial, but it's very important to understand this from an intuitive standpoint, that be careful, because when you try to make the system very, very fast, you end up using a lot of energy, and there is a trade-off. There is a clear trade-off that depends on the K that you adopt. And so if you want the energy spent to be small, then you have to go for large errors. If you want the error to be small, you have to spend a lot of energy. That's it. You cannot violate this. So now let's do this more formally, because now what we need to know to know is what kind of tools are available out there that will allow me to solve problems of this kind, but far more complex, 100, 200 variables, so on and so forth. So let's revisit this thing here. But this time I'm interested in controlling the angle, not the speed of rotation. So still I have a torque, and then I have a mark somewhere, and I don't know how to indicate this. I have a mark here, and I try to control. So there's a certain direction. I try to control this angle. So of course, torque equal d theta dt2. So now you have two integrators. It's what we call a double integrator. So if you have t that I call u, you have one integrator, and I have another integrator, theta. Sometimes people call this a pure inertia. Pure inertia. Okay, now we have to do something here that is trivial, but I'll do it very carefully because some of you probably are not familiar with the notation. As I mentioned to you, when we study control theory, we need to adopt a very general setting where the variables may not have any physical meaning, like here torque or theta, or use other letters. Typically, the input is u, the guts of the system, the variables are x, and the output is y. So let's do this. And another thing that we do is, instead of dealing with a differential equation of order 2, 3, 4, 5, or 1000, you want to deal with first order differential equations, as I already mentioned to you. So what you do, essentially you do the trick. You look at the equation, say, oh, this is a second order equation. So if I start at some point t naught, what data, what information do I have to have in order to predict what's going to happen in the future? So you need to know the value of theta at this point, and you know to have the value of theta naught. And then if you give it a certain input, you'll be able to see what the system will be doing, right? And you can keep doing this for all instants of time. So in general, you have theta, and this is called the state variables of the system, because they give you a measure, this sort of collapse in them, the information about the state of the system. If at any point I know these two values and I know the future value of the torque, I'll be able to predict everything. So keep in mind this notation, state variables. So it's only the minimum number of variables required to describe the evolution of the system. Now, what we do in systems theory is, instead, as I mentioned to you, instead of using theta or theta dot or rate of rotation, we use standardized notation. And we do this in an ad hoc manner. For example, we use the word x. Because you have two variables, you have variables x1 and x2. And now arbitrarily you could say x1 is theta, x2 is theta dot, but it could be the opposite. It's up to you to decide. So that's it. And now you stack the two variables on top of each other, x1 and x2, and you get what people call the state vector. And in this case, the state vector has dimension 2, state vector. And now, instead of writing this as a second order equation, you ask yourself the question, what is x1 dot? What is x2 dot? Okay, and this you call capital X dot. So now pay attention. X1 dot is theta dot, but theta dot is x2. So you put a 0, you put a 1, and you put an x2 there. So x1 dot is theta dot, or x1 dot is x2. All right, so this is easy. And then x2 dot is what? X2 dot is the input. So you don't see any term here, but you'll have to pick up the input u, which is the torque, and you put the 1 there and the 0 there. So x1 dot is equal to x2, x2 dot is equal to u. It's the same as that thing over there. So you have converted a differential equation of order 2 into differential equations of order 1. And why do we do this? Because now you can write simply, you can call this A, and you can call this B, and you write this simply as x dot equal to AX plus BU. And it doesn't matter if you have a system of order 1000, you have 1000 equations, but they are still written in this form, still in the same form. Exactly. So it's a very, very, very good advantage. Okay. So now pay attention to this. Suppose x dot equal to u. And I want to bring x to 0. If you do u equal to minus kx, then you get x dot equal to minus kx, which means that x of t is x0 e to the minus kt, t greater than or equal to 0. So the picture that goes with this is your system. You can call this the state. I mean, it's just dimension 1. And what you are doing to stabilize, it's to do what people call state feedback. You are feeding back the state. So like in the original problem of stopping the rotation, where x was the rate of rotation, all you have to do is to measure the rate of rotation with gyro compass and then go to the torque generator and boom, it will stabilize. This block here is state feedback. Why? Because you go to the state, multiply by a number and feed it back. That's state feedback. So now suppose in our case here that you have this plant, which is an abstraction of this one. How can I bring the states to 0? So thinking a bit about this, you could do something like this. Well, in this case, my dimension is 1 and it's u equal to minus kx. In this case, my dimension is 2. So I have x1 and x2. So why not do something naive, which is U is equal to minus K1 X1 minus K2 X2. See, you are doing state feedback. So you have this guy over here, X dot equal to AX plus BU, where of course you have here X1 and X2. So here you only have dimension 1, dimension 2. You have the U, and now instead of having one loop, you have two loops. K1, K2. And so hopefully this will work. It's a good guess. And again, this is what we call state feedback. State feedback. Now, is this going to work? Is it going to stabilize the system? Am I going to be able to control the performance in terms of having something that does not wiggle and stuff like that? That remains to be seen. Up to this moment, it's pure intuition. I had state feedback here. It does a great job. Now, of course, I didn't know how to choose the K, but any K would stabilize. And here I have K1 and K2. So the question is this going to stabilize the system? How do I compute the gains? How do I achieve a proper trade-off between energy and error being reduced to 0? So now U equal to minus K1, oh, I always want to erase with my finger, X1 minus K2 X2. Now X1 is theta, and theta 2 is theta dot. So you could do this, could look at this as this is rate feedback and proportional feedback. Okay. All right. So what should we do now? When you write U equal to minus K1 X1 minus K2 X2, because you have a good feeling that this will do the job by through proper selection of K1 and K2, people, again, they condense the notation and they invent the vector, which is K1, K2, and you simply write U equal to minus K times capital X. So when you compute this, you get minus K1, K2, X1, X2. So if you do the computation, you get exactly that thing. So what do I gain by doing this? Well, you'll be looking at very general problems. So for example, when I have X dot with bold, and then I'm going to stop writing bold, AX plus BU, and you have U equal to minus KX. Now pay attention. If the state vector has dimension Rn, this is an n times n matrix. If this has dimension 1, this is n times 1 matrix. Yeah. And this K, because this is a scalar and this is a vector, this is a 1 by 10 matrix. But the beautiful thing of this is that when you have more complex systems in which the input, you have 2 inputs, 3 inputs for output, like in case of the quadrotor, for example, no problem. If the dimension of this is m, you get a matrix of size n times m. But the way you write things is exactly the same. Now, so by going to this level of abstraction, I can write things in this manner. So when I implement this, I get X dot equal to AX, and now I close the feedback, minus BK X. So A minus BK X. The dimensions are okay. You see, this is n times n. This is n times 1, and this is 1 times n. So n times n, this is fine. All right, so this is what you get. The question is, how are we going to choose the matrix K and the components of the matrix K? So let's revisit the first problem to get some insight into this. And so suppose you are trying to minimize J. Okay, now so now you have two variables that you wish to bring down to 0. Yeah, that's suppose you want to stabilize about theta equal to 0. So you want to bring theta to 0 and theta dot to 0. All right. So when you implement this possible control law where you do state feedback with certain gains that we don't know yet how to compute them, then in the end, if x1 starts from somewhere and if x2 starts from somewhere, you have to have a measure of how fast they are decaying to 0. And again, you do the same thing. You compute the area under the square of each variable. So now you have two variables. So you should write x1 square plus x2 square. This will put a penalty on the deviation from 0. But now the energy kicks in and say, yeah, but I don't want to spend too much energy. So again, I put a term there, which is rho u square, and you get dt. And you are trying to minimize this by proper choice of this vector k. This problem is very famous. I shouldn't say by proper k. The way the problem was formalized initially was minimized by proper selection of these criteria. Here I'm already suggesting that maybe a possible solution that will come out of solving this problem is state feedback. But at the onset, you don't know. It could very well be that the solution would be something weird. Okay, so that's one Kalman first formulated this problem. He sort of wrote it in this manner. I want to minimize by proper choice of my control action this J that is sort of a trade-off between the deviation from 0, it's captured there, and then the energy that is spent. And that's what you want to do. Okay, now pay attention. If you want to go towards the more abstract setup, when you write x1 square plus x2 square, you can write it in this form. x1, x2, 0, no. One, 0, 0, 1, x1, x2, right? If you do this, you get x1 square plus x2 square. And you can call this a matrix, sorry, Q. So what you have here is a vector x1, and here you have the transpose. You have Q, and you have X. This thing is called a quadratic form, which already appeared in the case of the Lyapunov function. All right, that has nothing to do with this quadratic form. It's a compressed way of doing this. All right. Now, this may be a bit crude because you are saying, I want to penalize the deviation from 0 of all these variables. But you see, if you are trying to control a vehicle to go from here to 1 kilometer away. So you are measuring the distance in thousands of meters. And at the same time, you wish to keep the vehicle to look at some spot. You have two types of errors. The distance from the final point, measured in kilometers, and the deviation may be measured in milliradians if you want something very, very, very precise. When you put those numbers in here, and if one of them is on the scale of kilometers and the other one on milliradians, the milliradians are going out the window, okay? So that comes the first piece of engineering judgment. You have to put weights on this, okay? And well, essentially, there's a very simple way of doing this, which is the following. I expect during my normal excursions that x1 square should be maximum 100 meters and x2 2 milliradians. You multiply by factors that bring the maximum of 2 to the same number 1, for example, so that they are at the same level. Or you could say, well, it's far more important to point out with great precision in milliradians. So if the number is very small, it's going to be swallowed by the other one. You put a big coefficient there. So the way you do this, as you do the design, is the following. You have the input U, and you have the state X. And remember, in this simple example, X1 was theta and X2 was theta dot, and you want to bring them down to 0. You invent a number that you call Y. It has nothing to do with the output. You invent a number where you put the weights that I was talking about in here. If I cannot allow this variable to deviate very much from 0, and I'm very adamant about that, I pump up this number. If I can be more loose about the other variable, then the number can be a reasonable number, 1, 2, 3, 4, okay? So that's where the engineering judgment comes into play. You have on the, from the outset to define the relative importance of bringing the two variables to 0 quickly or not. And of course, you can write this in the form Cx, where C is Q1 and Q2, okay? So now, instead of using x1 squared plus x2 squared because it's too crude, say, wait a minute, I have to bring in those weights. Whoops. There you go. So instead of that, we are going to penalize at the state level the integral between 0 of y squared dt. So you have the input, you have the state, you concoct this artificial output, and this is what you are going to put a penalty on. Because when you select the K1 and K2, you already have the proper mix. If this is in milliradians and this is hundreds of meters, this number should be much larger than that one to bring out the importance of not letting the milliradians being swollen by hundreds of meters. Okay, so when you do this computation, then you can quickly show that this is the same as X transpose C transpose Cx dt, right? You go through the equations. And this is what people actually called Q. So when you look at the formulation of this problem, people actually write it in this form: minimize by proper selection of U, the integral between 0 and infinity of X transpose Qx plus rho U square dt. You even see it in a more general form when u is not a scalar. But this is what you see. And we ask the question, where did this q come from? It's from what I told you. That's where your engineering judgment comes into play. And you have to express your feelings and what you know about the plant exactly there. This is the famous linear quadratic regulator problem. Why? Because you are dealing with a linear system. At this stage, you only want to bring the state to zero. Because I'm in control, I want to do something much more complicated. I want to bring some variables to tracks. Okay, we'll get there. For the time being, we just want to bring them to zero. And quadratic, why? Because the criterion, there's squares all over the place. And it's called a regulator. In control regulator, the regulator problem is a problem of trying to bring variables to zero. It's called regulation. And then there's the tracking and stuff like that. Okay. So the big question now is, how can we solve this problem, right? So this was shown by Kalman long ago. Beautiful results. And he has said the following. If I'm given this system, and if I'm given this K and this rho, when I solve this problem, that looks horrendous, right? Because remember, you are not minimizing over a finite dimensional space. You are not minimizing, you are minimizing over a space of functions, for God's sake, all right? So, I mean, people in the past have been trying to do this using calculus of variations and stuff like that, but let's look at, you are trying, this lives in a space of functions. How are you going to find the function that will minimize this thing here? So Kalman has shown the form, the following thing. Under certain conditions that I'm not going to write down, but they are generic, almost always valid. Under certain conditions, and now this is the amazing thing. There is only one solution to this problem, only one. And in fact, it has the form of a feedback, of state feedback, which is amazing because it could very well be that when you solve this problem, when you do this numerically, it could spit out a function that you put on the system, but that is not very robust because you are not under closed loop. What Kalman has shown is that the optimal U is actually going to be equal times a matrix times the state. This is a beautiful result. Huh? So it's state feedback. This is the optimal solution. This is the optimal solution. The big question is, okay, fine, but how do I compute K? In other case, K, in our case is K1 and K2, but in general, you could have a K with dimension 100 or 200. And now comes the cryptic part, because it's the mathematical part, the result. I don't know what your reaction to this will be, but that's what the theory tells you. Don't panic, because whatever I'm going to tell you, MATLAB will solve it for you. I mean, once you give A, once you give B, once you choose Q, that's where the judgment comes into play, and the row, boom, it will solve it for you. So what Kalman has shown was the following. Under certain generic conditions, he has shown that under these conditions, there's only one positive definite solution. Remember, you know what a positive definite matrix is, right? So P is positive definite if Px is greater than 0 for x different 0. And then he writes this famous equation, ATP plus PA minus E B rho inverse BTP plus Q equal to 0. My God, what's going on? Okay, it's called the Riccati equation. Riccati. So Riccati was a count. I think he was Italian, and he studied these kinds of equations. Riccati, celebrated Riccati equation. So what Kalman has shown is that under these generic conditions, there is only, so you see, Q is given by U, B you already know, rho you know, A you know, all you have to do is to find P. And he said, under generic conditions, there's a unique positive definite solution to this equation that MATLAB will find for you. Look, and then the optimal solution is of the form U equal to minus K, where K is equal to R inverse B transpose P. Beautiful result. So now it doesn't matter if the size of this matrix is 10 or 20 or 30, the order of the system could be very, very large. And the result is exactly the same. So now let's apply this. Okay, all of this can be done in MATLAB. There's a command for which you enter the dynamics of the system, you enter the Q, and it spits out the K. State feedback, control law. So let's revisit our first naive example. What was the first example? It was x dot equal to U, right? Where you had the satellite spinning, R, and here you had U, which was the torque, and you wanted to bring the rotation down to 0. So you had x dot equal to U. All right, let's solve this. So you have to write it in the form x dot equal to AX plus BU. Well, in this case, it's trivial because A will be equal to 0 and B will be equal to 1. That's piece of cake. And if you want to minimize the integral between infinity, you don't have much choice here. You just put x squared dt plus rho u squared dt. So you don't have the problem of having more than one variable and trying to set an equilibrium on them. So this means that if you write x squared as x transpose qx, then obviously q is equal to 1. All right. So when you go through the Riccati equation, minus b transpose p plus q transpose q equal to what you get? A is 0. Boom, boom. Now b is equal to 1 q, so you get minus p square over rho plus 1 equal to 0. So this means that P, there are two solutions. One is positive. Huh? Just a second, please. Yeah, I could see some flickering. Yeah. So when you go through the proof of Kalman and it tries to solve the problem, P is somehow related to an energy in a certain, let's call it Lyapunov function. It's hidden in the proof. And when he proves the theorem, then he shows that there is a unique solution, and the solution is obtained in this form where you solve this Riccati equation. It comes out naturally. So yeah, there's P. Are we online or not? I shouldn't say anything foolish at this point. Hmm? Yeah, that's it. That's P. You see, some of these results can be used using something called dynamic programming that was invented by a gentleman called Bellman. And where the P was somehow associated with the cost that is remaining. So I start this optimization problem, and he had a very interesting way of doing this. But at each instance of time, he said, if I use a certain solution up to this point from here on, what's the cost associated with driving me there? And P was associated with this terminal cost. So the ideas were there, but you really have to get into the guts of this thing. But it turns out that the solution is beautiful, actually, right? This is very important. When you solve a true, yeah. When you solve a problem of this form, so can they hear me now? Huh? But can they hear me now? Can they hear me?
Yes.
Okay. Yeah. So when the problem was first derived, the problem was minimized over a certain time interval. It's a more complicated problem because the gains are going to be time varying. It's even more. So you don't get this is an algebraic Riccati equation. Then you get the differential Riccati equation. But they shown when the time horizon stretches out to infinity, then when time flows, then you get a steady solution for P, and then satisfies the algebraic Riccati equation. Okay, so now P is equal to 1 over rho. No, P is not equal to 1 over rho. P, which in this case is a scalar, is equal to square root of rho. So when you compute K, which is, it's here, rho inverse B transpose P, you get 1 over this, which is what we had before when I gave the simple example. So, so this tells you, again, the obvious thing, when the energy is very cheap, then K, the optimal K is 1 over rho. Remember when I determined the optimal K by computing the, how do you call this? The extremum point, the minimum of that function, I got 1 over rho. Why? Because I postulated that the solution would be U equal to minus KX. Here, when I tried to solve the problem at the beginning, I didn't know that the solution would come out in that form. It turns out to be. So it's I don't know. That's the way the world was built. God's invention, or however you may wish to call it. For these types of problems, the optimal solution exists, and it's in the form of a state feedback, and you can actually compute the K in this form. So now, for example, if you go to the more complicated case where you are trying to control the angle of this thing up in space. So what did you have? the derivative of omega was the torque, which is u, and then another integrator, and you have the angle. And then you can write this in the form x dot equal to x plus bu, where x, now I don't remember, I think it was psi and omega, which is x1 and x2. You can formulate the problem, you can put penalties, and then in the end you get u equal to minus k1, k2, x1, x2. So naturally you have k1, and naturally you have k2, and that is your controller. Okay. The big thing is, how do you know that this system is stable? Kalman showed it for you. The solution that you got, you call it stabilizing. It will stabilize the system. All right. If you want to know more in mathematical terms how you assess the stability, you see. So this is not terribly important at this point, and you have u equal to minus kx. Then you have in closed loop a minus bkx. So you could call this x dot equal to a tilde times x. So I don't know if they have studied eigenvalues, and maybe not. Huh? You guys know everything. So if the real part of the eigenvalues of a tilde are less than 0, the system is stable. Okay, but that's another story. Now there's this is not psi, this was theta. There's an intriguing thing, because you say, okay, but this is just a regulator. But suppose now that I want to track a constant reference. How do you do this? You do the design for the regulator, and then you do a dirty trick. You do this. So you start there, omega, and this is u. You have omega, and then you have theta. Now I'm going to have the K2 here. Oops. And now I'm going to do a trick. See that guy coming from theta multiplying by theta 1? I'm going to stretch that path. This is minus. Put minus here. Put the K1 there. So I have not changed anything. Okay? Because this is K minus K2 times omega minus K1 times theta. And now, boom, I put the reference. And it becomes a tracker. So that's how I convert it into a common control scheme. So the way you do the LQR design, when you want for one of the variables to track a certain reference, you write it in state space form. Hopefully, one of the variables is whatever you wish to control. You go in MATLAB, solve, you get the K, you implement the feedback, and then at the end, you bring the loop of the relevant variable so that you can compare with the reference, and you have a beautiful system here. Okay, now we should stop at this point. I have not completed yet, because now I have to give you the intuition. Suppose you design this and you give it a step, and you're like, oh God, I did something wrong. How am I going to correct this? So I have to give you the intuition for the design. So I think the main message I want to leave with you is there's a beautiful theory for linear systems that will allow you to design controllers for arbitrary plants with very large dimensions if you can measure all the state components. Because remember, U is a combination of the state variables. You might ask the question, what if I cannot measure all of them? Because you may have an interesting structure in space. You are only paying attention to the position and orientation, but there are some variables inside that probably you don't want to measure directly. That's a different story. Then there's something else you have to do. But for the time being, this is what you can do, and it becomes very straightforward because you can go to MATLAB and simply put that in. Now, as with any advanced tools, at some point, as I said, the engineering judgment must come into play. And this is why I don't like some of the stuff that is going on, that some of it is quite serious. But teaching the students how to download apps and simply play with things and see what happens, this is not solid engineering. I mean, when you have you have to understand the tools, and then at some point you have to put your intuition, your judgment into it, okay? So this is very important. All right, we'll continue next Tuesday, I guess, right? So, yeah, and then probably we have to give an extra lecture on Wednesday, but we'll let you know, probably, because I'm a bit behind. Okay, so you have any questions? I understand this is a bit new to you, but. So any questions from our friends online? Maybe not. Here? This is, I'll give you an example. Suppose your system, you have an idea where the variables are. For example, if you are trying to control theta and theta dot, and you are trying to bring them to 0, probably when you engage the controller, you could say something like, well, theta probably is in this range of variables. So let's say theta max is, for example, I don't know, X radians, okay? And theta dot max is Y radians per second. You know that. So what you do here is you could start by, if this is theta, and if this is theta dot, you could put a number here, which is the inverse of this Y radians per second. And here you put, no, it's the other way around. X radians 1 over Y radians per second. Why I'm doing this? Because now this guy has excursions between 0 and some other value. The maximum value, where the maximum value of where the maximum absolute value is this. If you divide by X radians, then the maximum absolute value of this will be 1. And you do the same to the other one. Now they are on equal footing. Now you can compare apples with oranges. See? And you don't have one dominating the other one. Because it could very well be that with the scales that you adopted, for example, this guy would essentially kill the other one. Like I said, if you are trying to move things, and the range is involved on the order of kilometers. And at the same time, the capsule has to maintain an accuracy of milliradians. When you put the things there, the milliradians will be off, will go out. You cannot. So that's the first thing. There's a famous, the person that first came up with this methodology was someone called Bryson. It's called Bryson's rule. That's the way to start, but it's not sufficient. But that's a good way to start. Okay. And so then I have to teach you how you evaluate the performance, the linear quadratic regulator. And in case you are not happy with it, how do you choose the row 1 and the row 2? How do you choose that? Okay. So no questions from people online and from people here? What other questions?
So can we choose the PID gains?
Yeah. I'll show you an example where you have to design a PID controller, and I'll let you know how the gains for that complicated case where you had the third order system, you didn't know how to choose them, and I'll show you how to use LQR to easily come up with the gains, right?
So here we are dealing with the cylinders that we're trying to control its motion, right, sir? Like for individual cases. What if we have two different cylinders that we are trying to reduce the speed to 0? So
You mean these things rotating? But if they are separate, you have two separate controllers. Maybe I didn't get.
terms in the AX plus BU that rejection will include those terms for two different cylinders.
No, if the cylinders are different, they don't have anything to do with each other. You have two separate controllers.
Two separate equations.
Yeah, they are completely separate.
But if you're talking about something like two different surface vessels that are trying to track the same target, so in that case, we can model that ship problem as this same scenario, right, sir? So in that case, how would you track two different ships?
What do you mean by track?
Let's say we have one target and you're trying to make two ships move to that particular reference point.
Okay. So you have the target here, right? And you have the ship 1 and you have the ship 2, right? You are trying to make them track like this? Is that so?
More like two ships are
Tracking a third ship so that the third ship's theta is what those two other ships are trying to track. So in that case, how would you model? Do you have separate controllers individually trying to do it, or?
Well, I mean, the easiest way to start is to have each ship on its own. So this one tracks this one, and then the other one is trying to do the same. You may get into trouble because they may collide. So you could, for example, say, I want these two ships to track that target in a nice way. For example, if the target is doing this, I would like for these two ships to evolve in such a way they, for example, they could be side by side and tracking the target. This is completely different because now there's some interaction between the two, and you have to bring that into the picture. It's another additional thing that you have to do, right? So the way, okay, I'll give you a simple example. Suppose you have a target doing this, okay? And you say, and you know more or less what this guy is doing. Suppose it's heading east. And for some reason, I would like for one ship to go on the left of the target and the other one to go on the right. So this one could come from here and do something like this. the other one could come from there and do something like this. Then you could request them to be aligned in this manner and at a certain distance from the target, right? You are talking about two separate problems here. So the first problem is to bring each one of the ships to these paths. This is called path following. And then once you have these ships very close to these paths, then you have to kick in the coordination part, where you estimate this distance, you see if the vehicles are actually shoulder to shoulder, they have to talk to each other, and they have to move up and down, speed up or slow down so that they synchronize, and they establish a formation that is behind by a certain delta. That's a separate problem. In order to do path following, one of the simplest ways, so let's look at this guy now, is you go at a certain speed, and of course you have to control the speed, and the only thing you do is to control this heading angle so that you do a smooth transition here. This normally is done using Lyapunov theory at the kinematic level. And finally, when you get to the guts of the system and the kinematic system tells your ship, go with a certain heading, that's when you have the linear design. But this is a very simple case, right? But there are many examples where you have a plant with many inputs and possibly many outputs. And the theory of Kalman still goes through. There's no problem at all, okay? So, so you send with measurements of states, you can say, no, you said, no, you can't say such a thing. Okay, so let's examine the sentence. One can say LQR is better than PID. No, no. If you have a physical plant, and I'll show you an example next time for the Nomoto model, where in a Nomoto model, you already have an integrator at the output, so you have steady state feedback error equal to 0. So with PD, you can do whatever you wish to do. But let's suppose now that the rudder has an offset, you have to introduce another integrator. So you have PID. We have PID. I'll show you how that PID comes out naturally of solving the linear quadratic regulator problem. So the PID is a particular instance of a general state feedback control law. It's very, now I warn you, it's very delicate to compare controller methods. But I'm going to I have a new method, number 2. I'm going to compare with the method number 1 developed by another group. Oh, mine is much better. How do I know? How do you design the using method number 1? Tell me how you design. Maybe you design in a manner that is biased. So I designed using method 1 without much engineering judgment. So there's no surprise that with my method I'm doing much better. So it's always a bit tricky to compare. So now you cannot say that LQR is better than PID. What I'm saying is, for certain classes of problems, you solve the regulator problem, and the solution that naturally emerges looks like a PID. But that's beautiful, because now you have a way of choosing the PI and the D gains without playing in the computer. It's not ad hoc. And don't require linearization. No, all that I have presented so far is for linear systems. Okay, now, Sivaraman, please go ahead. Hello? Okay. Okay, good, you said. In co-applicative, house speed, yeah. How speed is controlled? What? I mean, I have shown you an example, right? That was with the torpedo. So there's the thrust, there's the speed. So the thrust minus drag, I'm going to assume it is of this form, is equal to m v dot. That's your system. So now you have two ways to go. It's a nonlinear system. You may use a nonlinear controller. If you used to use a linear control law, then you say the following. I want to control this ship about a certain nominal speed, which is v equal to v nominal. And you linearize the system about this particular condition, and then you get a linear system, and then you design a linear control law, which in this case is trivial. You don't even have to use the LQR regulator. You don't have to do that. For the case of U-turn, have same speed. No, that's a different problem. If you are trying to do cooperation between two ships, and if you want them to go along parallel paths, in order for them to synchronize like this, they need to go at the same speed. V1 is equal to V star, V2 equal to V star. If you want to do cooperation for other kinds of trajectories, for example, suppose you want to do this. You have the center, and one ship goes on this radius, R1, and the other gun goes on this radius, R2. I mean, it's obvious that in order to be synchronized, the speed of this one, V2, should be different from the speed of this one, according to the ratio of the radii. So the beautiful thing, and Avanish has just completed simulations of this, where somehow you don't have to tell, and you could have three, you don't have to tell each one of the ships or robots at what inertial speed they should go. You tell one of them at what speed it should go, and the other ones will learn automatically what speed to achieve in order to have this kind of synchronization. Okay? Welcome. So any other questions? Oh, all right. Okay. There's some saving. So I wanted to finish the LQR today, but you know, it's always important to study these intuitive aspects. I'll get back into this. give you one or two examples of things that you cannot possibly achieve with any control. Okay, I'll show you. Yeah.
மொத்தமா இன்னைக்கு அம்சம் இன்னைக்கு போனா மட்டும் ஆமா ஆமா இதெல்லாம் பசங்க விசாரிச்சு ஜி சொல்லுங்க ஜி நான் 301 இருக்கேன் ஜி நான் முடிஞ்சு 2 முடிஞ்சு உட்காந்துருக்காங்க ஜி சரி சொல்லிடு ஓகே சொல்லிடு சரி தப்பு சொல்லிடு ஓகே ஜி சரி ஓகே இப்போ உடனே சொல்லிடுறேன் சரி ஜி மெயில் அனுப்பிச்சுடா
Yeah. Okay.